replace. Okay.
Yeah. And this is the same.
Okay, great. Yeah, so I'm happy to be able to provide a bit of context on the protocluster survey that gave rise to this spectacular object and TSC detection that Daji was talking about. I'll just take one moment to remind Joel Primack that it was about 20 years ago that I cold called him from Caltech with this new population of sub-millimeter galaxies and asked if he could help us model and simulate them. And we put Patrick Johnson to work on that with his new Sunrise code, and some really neat early simulation results emerged from that. And here we are 20 years later using these same sub-millimeter galaxies to find really spectacular protoclusters in the early universe, and leading to by far the highest redshift detections of Sunyaev-Zeldovich. So this is the crown jewels of our survey is SPT 2349 at redshift 4.3. There's a little simulation that Doug Renahan and Arif Babul put together for us, taking the initial 14 galaxies that were found in the core and using them as initial conditions for a hydro simulation to see what would happen as you evolve this forward. And you can see the results. It's the biggest mega merger that's ever happened in the universe, probably. So a little bit of intro. Galaxy clusters are the building blocks of large-scale structure. They're found out to redshift 2 now fairly regularly, and they're characterized by this hot X-ray gas and the SE signal that results, and very tightly coupled to the mass. The progenitors of these clusters are called protoclusters, and they're easily traced in simulations. And we think we probed them observationally, but what we typically do is find overdensities of galaxies and then bend over backwards to try and figure out what the mass scale is of this overdensity of galaxies. And no one ever really knows if it's an actual protocluster in any real sense or what it will evolve to. But it's an emerging field. So the state of the art is wide field Sunyaev-Zeldovich surveys like the SPT survey. These are shadows on the CMB. You can also see the white emissive sources, which are the source of our protocluster sample. The most recently from the SPT 3G survey, which is the stage 3 SC, we're expecting sort of 10,000 clusters now to a mass limit of 10 to the 14 from the full survey. There's a recent paper of the first 100 square degrees and a sample of 500 clusters extending out to redshift 2. So I just wanted to point out, building on what Daji was saying, this SC detection of our protocluster at redshift 4.3, it's way above the self-similar scaling that you get from the expectations from low redshift clusters. But because of that, even if we think that most of that energy is coming from preheating from AGN, it actually masquerades as a fairly massive cluster, 5 times 10 to the 13 solar masses in cluster SE space. So in principle, it could actually be found in a wide field blind survey, whereas, as Daji pointed out, all the redshift 2 protocluster Sunyaev-Zeldovich detections that people have struggled to get, all 3 of them there, are way harder than you'd even optimistically expect if they followed self-similar scaling. So this potentially, I think, really opens up a new field of, because of preheating in the early universe, in early cluster environments, potentially opens up a new field. So on the same plot, the SPT 2349 would be down there. In principle, it's almost detectable with SPT 3G or Simon's Observatory, and would be detectable in a dedicated wide field LMT, a large millimeter telescope in Mexico survey. And I just highlight the unfortunate demise of CMB-S4, another casualty of the current situation here. So here's some context here, a little cartoon that Caitlin Casey put together a while ago, just kind of piecing together the ingredients of simulations people were doing 5-10 years ago now on protoclusters from simulations, and asking if they can be traced by sub-millimeter galaxies, basically very luminous, dusty galaxies. So you see different epochs. At the earliest epoch that we're talking about here, redshift 4 to 7, let's say, we're seeing all the action in the core, very strong star formation rates in an inside-out formation of the core. And then some of the cluster ellipticals are starting to form as luminous bursts further out in the cluster at redshift 3, and then we know the rest of the history. So this is actually borne out well in observations, both the very high redshift epoch and the redshift 3 epoch. I think this is what massive clusters actually look like. So this opens up obvious answers to the question, why observe protoclusters in the submillimeter? Early assembling galaxy clusters are forming lots of stars in their core. And importantly, the wide field submillimeter surveys we now have access to, like the South Pole Telescope, can find them very efficiently. You can see the emissive sources on the primary CMB there. And importantly, some massive protoclusters, like our crown jewel 2349, can only really be found in the submillimeter. I had a student, Kaya Roderman, who studied this in the optical in 2021 as part of her thesis. And you can find it in Lyman break galaxies. It's a reasonably high contrast, but the core is basically invisible. It's so dusty, whereas it stands out like a sore thumb in the submillimeter with 7,000 solar mass per year star formation rate in this dense core. And it would, in the optical, it would appear in your catalogs of Subaru LBGs, but it would never be the first system that you would go study. Yet it probably is one of the most massive and extreme environments in the universe. And this, where did it come from? We had a survey SPT protocluster, rather than the SPT-SC, the survey they were found in. Over 2,500 square degrees, the first iteration of SPT, relatively shallow. We found 9 protocluster candidates, which we later found to be at redshifts between 3 and 7. And the way we figured that out was ELMA follow-up of them, find redshifts with spectral scans, and then resolve all the dusty sources. And here you can see one iteration of the spectra, C+ spectra of all the galaxies in the core. They're now numbering over 30 in this 100 kiloparsec core. So I just wanted to point out that high redshift in itself, the median redshift of these protoclusters is 4.5. That already implies some kind of a special environment or accelerated evolution. Even if we haven't studied the outer regions of these things, they have to live in very massive halos and probably protocluster environments. There's a nice paper by Doug Renahan last year that showed this assembly bias, that the star formation rate density in protoclusters is way higher than the field, and that's what we find in these systems. So I just want to point to 2 key plots, and I'll just outline a couple aspects of a few of our protoclusters in this way. One is the assembly history of halos, basically from redshift, plotted as cluster mass. The gray is the coma cluster's likely progenitor with redshift, and all your favorite clusters at around redshift 1 to 2, and then the SPT survey. And our dynamical mass of SPT 2349 sits nominally above that relation. We'll look at this again. But the other key plot is how concentrated and intense the star formation rate is. So star formation rate on the vertical axis and on-sky area on the horizontal axis. And the black curve is an early rendition from the Miller paper in 2018 of 2349. All your other favorite protoclusters that have been studied are way over here, many orders of magnitude less intense and dense. And we get the mass of this thing both from the velocities of the members, which look fairly virialized in the core region, and also from abundance matching from all those galaxies, getting fairly consistent results at 1 times 10 to the 13. So all those galaxies in the very core are likely to merge together. We added all 30 galaxies and needed to dumb down the resolution a bit, but the same thing happens with 30 galaxies. Almost nothing survives after a few hundred mega years. I'd point out this was last year's 4th favorite protocluster at the first structures meeting in Paris. It's a super interesting system. Okay, so I just wanted to say a little bit more about the preheating. So we found a luminous Radio-AGN in the core a couple of years ago. It yields an estimated energy input of around 2 times 10 to the 45 ergs per second. Shocks from the radio jets could yield even more energy injection, and then there's lots of star formation, but it's probably less efficient at heating ICM. But it's really a smoking gun of the ICM preheating, and as Daji pointed out, this is probably the main reason we see the SC effect from the superheated hot ICM in the system. And then recently, we're working on an updated paper with now 4 radio-AGN in the core, 3 right in the middle of the ICM SC that we're seeing. Okay, so I just wanted to finish with a few other of these systems. This is a Galaxy's Workshop, of course, not clusters. And I wanted to point out that these protoclusters host some of the most extreme galaxies in the universe. So if you want to find the really crazy, incredible high star formation rate galaxy examples, they live very nicely in these systems. One is in this redshift 5.7 system, 0348. There's 3 bright SMGs in the core. The brightest is crazy. It's 30 millijanskis and at scuba wavelengths, or 4,000 solar masses per year, and some satellite SMGs. Interestingly, it's also the only other radio-AGN in the core is from this one. So it's even though it's at much higher redshift, we might try to see if SC is detectable from a superheated ICM. And just because of that extreme bright central source, it actually rivals all the other ones we know about in the core region, which is pretty incredible in itself. And who knows what the actual halo mass is, but there's a lot of stuff going on in this thing at almost redshift 6. And then 2 other ones at redshift 4, which keep getting ignored because all my students like working on the crown jewels more than the next best thing. But 0457 here is within spitting distance of the other 2 highlight ones from 2018. And it also has a fairly incredible central submillimeter galaxy and many satellites. And then this weird system 2052, which in molecular gas mass, it rivals everything else we know about in the core. It's an incredible amount of molecular gas, mainly in 3 of the most spectacular galaxies we know about in the universe. So this is another just crazy system at redshift 4 found by SPT. Okay, so my ruminations on protocluster cores and BCG growth to finish here as a summary. So there's no question that massive clusters, and certainly their BCGs, can have an incredibly active and violent gas-rich mega-merger formation epoch at redshift greater than 4. This isn't necessarily how we thought BCGs formed. We thought they formed much less spectacularly over a protracted period of time, not in some mega-burst, mega-merger that happens in 200 mega-years. I think this is interesting. It's not clear how typical this is in massive clusters. Sure, the duty cycle is super short, and we're preferentially finding these things because we're searching in the submillimeter. But these examples are still about 1 per 100 square degrees. So they're very rare on the sky, but they may represent an important phase of the most massive cluster formation. So each of these fields is interesting and unique. We're trying to get more of them published, and we should definitely search for TSE in all these SPT systems, and maybe consider looking for similar system in blind submillimeter surveys. And finally, I think, as Daji was pointing out, we're learning a lot from studying these cluster simulations, TNG cluster and the Manhattan suite we're starting to look at, and others should all be studied and compared in detail because there's a lot to be learned there for comparison. Thank you.
Questions? Can we ask the next speaker to come up and start to be ready?
Very interesting. I was wondering if we know something about the morphology of the galaxies in the protoclusters. Do you have any evidence of?
Well, we have recent JWST data on this system. We haven't really looked that closely at the morphologies. There's everything in there. There's giant extended stellar disks over almost 20 kiloparsecs. There's also things that look like little red dots in there with the same colors as all the other galaxies we already knew about. So there's probably everything you can imagine all packed into that central region. Dwarfy satellites around the most massive ones and everything.
Thank you.
actually wondering about the morphology of gas. Can you actually measure, like, or get the sense of like any elongations
Of the SC, you mean?
of SZ?
Well, Daji claims that it's actually quite concentrated potentially around the 3 Radio-AGN morphologically, but that's not in the paper and is work in progress, I think.
Yeah, because I think it's a bit interesting to see how these SZ signals and also morphology depends on sort of mass accretion history of the halos in simulations.
There's potentially smoking gun that the 3 Radio-AGNs are really the heating source, but that's speculation at this point. Sorry, Daji, if I put too many words in your mouth there.
Thanks, Scott. I was wondering if you have looked at gamma-alpha emission, you see relatively large gamma-alpha blobs in the region.
There is a big Lyman alpha blob in this core, but it's offset from the BCG and all the action by about 50 or 100 kiloparsecs, I can't remember. It's in the corner of the core, there's a huge Lyman alpha blob, but it's not in the center.
They should be offset because the center is obscured.
Yeah, well, that's what I was going to say, is probably obscuration effects, but
Yeah.
there's a giant Lyman alpha blob on the periphery of the cluster core.
Thank you.
I was wondering whether any of the simulations actually recreate some of the most extreme star formation, and then the second suggestion maybe for the audience is to explore maybe clustering of the extreme star formers, because your map is just so suggestive, right? If you look at the whole thing, just the star formation, and you clip at the very high level, you see this clump. I was wondering whether any of the simulations reproduce. Well, first of all, do they even make 4,000 solar masses per year stuff? Secondly, if they do have things that say above threshold, say up at 200, 300, something very high, is the clustering behavior such that it might be an interesting diagnostic? I've not seen a clustering analysis of star forming.
Yeah, I don't know the
Has anybody done
answer.
it, by the way?
I don't know.
Has anybody done that? I don't know if someone's done it. Okay, great.
Okay, well, on that, why don't we thank Scott one more time?
Thank you.